Maybe just to add to this, like the really easy way to think about this is data parallelism means you're chopping your data set into multiple small pieces, and each miner gets a small piece of the data set. And pipeline parallelism means you chop the model, so the actual compute that needs to happen, up into lots of small pieces, and each miner takes a small piece. And if you look at some of the other subnets or a lot of the other projects out there, data parallelism, what people usually refer to when they talk about federated learning, where it's like each miner sees like a small subset of the data set.
The pipeline parallelism is used a lot in data centers. It's the only way you can train a GPT-4. You can't do it on a single, it doesn't matter how powerful the GPU is, these models are way too big. So pipeline parallelism is very well established in the context of centralized training runs. By centralized, we mean sort of geolocated in the same data center. They have the benefit of being connected by very high bandwidth, basically networking cables, NVLinks or something like that. So CLASP, it relies on basically, because miners don't know whose data they're processing, because you've got this coupled system arranged in layers, you're basically picking up the output of the previous layer. Someone in the previous layer has an output, you take it as your input, and so on and so forth. Now, miners do not reliably know whose work they've taken on, and they're going to continue. And as a result of this, the CLASP is built on the fact that you basically have all of these sub-pathways that can go through our network.
Welcome to the Ventura Labs podcast. Today, we're joined by Felix and Steffen, the minds driving Subnet 9's leap onto IOTA. We'll dig into how their orchestrator splits massive models into layered groups, pipelines data across miners, and keeps everyone honest through shadow audits and the potential for CLASP-based loss scoring. Expect a fast-moving tour of activation hacks, compression tricks, and hard lessons learned while redefining distributed AI training, and why being early still means everything in this space. Now, back to Felix and Steffen with the 50th Ventura Labs podcast.
All right, Felix, Steffen, it's good to get you guys on the podcast today. How you doing?
Good.
I'm great, man. How you doing?
All right. You guys have had, in the past 3 weeks or so, one of the biggest transitions in Bittensor in Subnet 9. It's one of the legacy subnets that everyone knew about. You recently transitioned to IOTA, so you're tackling the same problem, just in a different way. What is that problem you're trying to solve with Subnet 9?
What we've been trying to solve since the beginning of last year is large language model training, which means it's a very computationally expensive process, one that is typically only available to the very well-endowed and well-funded institutions. And I believe it's one of the reasons that Bittensor itself was created. Yeah, it's very tricky. There's an enormous amount of technical complexity to train these models to a high standard. Of course, the bar is always increasing, which makes our work even more difficult. But where we began, if I'm going to give you a little bit of a whirlwind tour of that, is we had a different articulation of pre-training in the previous version of Subnet 9, where the miners were forced to train an entire model in isolation, a little bit like a Kaggle competition for the data scientists in the audience, with a slight caveat. And the caveat is they're allowed to copy off each other. This was possible because in order for miners to be eligible to receive rewards, they had to publish their model to Hugging Face, a public repository. And that means that all of the other miners have an opportunity to download someone else's result and train it further, or do some clever optimizations and make it a little bit better. So it was a little bit like a Kaggle competition, but it wasn't really that everyone was an island. It was an island with some sort of ferries that would allow people to get from one place to another. However, what we learned, and we really pushed that design pretty hard for a year and a half almost, what we learned was that it's just at a certain size of model, it becomes too expensive. There's a lot of duplicated work because everyone's kind of cooking their own version of the model. And so what we looked at is distributed training, which is something that Felix and I are very passionate about. And distributed training is where, how can you have a collaborative process where everyone takes a little bit of the work and then you can combine that work, pool it all together and get something which is, the sum of all of that rather than the best of all of them. So that's a slightly different vision. And that's kind of how we landed where we are today.
And this new architecture assigns layer groups to each miner pool. can you explain what a layer is in this context?
Yeah, so in a machine learning model, you have something called transformer blocks, or we just refer to them as layers for conceptual ease. But the bigger the model, the more layers you have. So let's say quite frequently in a 70B model, you might have about 80 layers. And the data flows through the network or through the LLM, just layer by layer. So in principle, it's feasible for one miner to host an individual layer rather than hosting the entire model. Because if you want to train, 70B model at once, you need a whole lot of upfront investment to build the infrastructure, to have enough GPUs to be able to do that training. So by just splitting it off into smaller sections, you're able to enter that with a much lower initial threshold. And by assigning, each layer to a set of miners, we can just support people with much lower initial cost, and therefore we can train much bigger models because we can just keep adding layers without increasing strain on an individual miner.
And in this layer system, is each layer a different part of the data set?
No, so in this case, each layer is a different part of the model itself. So the LLM itself consists of lots of layers, and each layer is just one small part of the big model. The data set is kind of a completely separate pool of data that we take data from to send through that model, if that makes sense.
Yeah, and I think to expand on that with perhaps an analogy, imagine you've got a car manufacturing plant with a large assembly line. And at the beginning of the assembly line, you just have the raw components. You just have the access and a few plates of steel. And by the end of it, you have a recognizable vehicle. And what the model is basically doing as the data flows through layer by layer is it's adding more and more to, basically it's applying more and more computation until you get to the end and you have sort of the complete product. So the miners are instead, they're like assembly line workers where they take a specific section of the workload, they perform that work, and then they pass it along the line. So that's really the idea here. And it allows, once again, this to be more of a group effort rather than a winner-takes-all effort.
And in that group effort, how is the data set distributed amongst the miners?
So in this case, we just forward one sample out of this data set, and you can really imagine the data set as, almost as if you're just taking one big book, and each sample is one sentence. So you'll forward one sentence to a miner in the first layer, which will then do some computation and forward it to the miner in the second layer, and so on and so forth. So basically, the one data sample, the one sentence, will travel through all of the layers in the network to then produce your kind of desired output. And then you'll take the next sample and also feed it through through all of the layers, if that makes sense.
An additional caveat to that actually is, so what we're describing is called pipeline parallelism, but there's a second component called data parallelism, which I think is also kind of what you're asking about. Data parallelism is something that has been much more explored as a concept. And basically, a simple version of a data parallel network is one where every miner on the network has a full copy of the model. So they have all of the layers. Again, per Felix's point, that's more expensive for a large model. They have to run really powerful hardware to be able to process so many layers of the model. But what happens is, if all of those copies of the model are training on just different shuffles of this big book, and then occasionally they will share their information and synchronize so they benefit from the learning of the entire group, that's what data parallelism is. And we actually use that as well. So we basically chop this large model up into sequences or sections, which we call the layers. But each layer, we actually have 50 workers in each layer as well. So it's called data parallel and pipeline parallelism, which allows us to kind of get the best of both worlds. The barrier to entry in terms of cost and complexity remains low because we break the model into small chunks, but we also get the accelerated learning process that comes with having a group of people all processing different pages of the book or different sentences of the book in sort of synchronization.
Maybe just to add to this, the really easy way to think about this is data parallelism means you're chopping your data set into multiple small pieces, and each miner gets a small piece of the data set. And pipeline parallelism means you chop the model, so the actual compute that needs to happen, up into lots of small pieces, and each miner takes a small piece. And if you look at some of the other subnets or a lot of the other projects out there, data parallelism, what people usually refer to when they talk about federated learning, where it's like each miner sees like a small subset of the data set, so a small chunk. And what we're introducing with IOTA, I think for the first time, is pipeline parallelism, where not only do we chop up the data set, but we also chop up the model.
When you say introducing for the first time, this means the first time, like, ever that you're aware of someone implementing this, or first time in a decentralized setting?
The pipeline parallelism is used a lot in data centers. It's the only way you can train a GPT-4. You can't do it on a single, it doesn't matter how powerful the GPU is, these models are way too big. So pipeline parallelism is very well established in the context of centralized training runs. By centralized, we mean sort of geolocated in the same data center. They have the benefit of being connected by very high bandwidth, basically networking cables, NV-links or something like that. Doing it in a fully decentralized setting means you replace those high bandwidth interconnects with the internet. So you're just sending things over the wire, which presents a very big challenge because you're sending a tremendous amount of data across the world, which is of course very complex and also very expensive and slow, which is one of the primary challenges for the architecture. In terms of where else this has been done, to our knowledge, no one has done a pipeline parallel decentralized training run in history. So this is actually a world first.
There you go. Well, congratulations on that.
Thanks.
And in this subnet, the product, or what you would sell, is the orchestrator aspect of it, in the sense that that controls what model's being trained. Can you explain how the orchestrator aspect works of this? And currently, the subnet owner, you guys, are the only orchestrator on the subnet.
Great. Yeah. I'll take a stab and then he can correct me when I'm wrong. So first of all, Felix designed the orchestrator, so he's the mastermind behind this. The orchestrator is responsible for basically the state management of all of the workers in the network. When miners register in the subnet, they have to sign up and basically announce, hey, I'm here, I'm ready to work. And then they're going to be assigned to a layer in the model. So they're going to be placed somewhere in the network, which is where they're going to be doing their work. Secondly, what they're then going to be doing is they're going to be constantly asking the orchestrator, hey, what can I process? Where's the data for me? And the orchestrator is responsible for identifying the data that is ready for that miner and that layer to work on. And so what this actually looks like is we have a massive S3 bucket. So we've got a big storage bucket. And what happens is the miners are constantly uploading, downloading from that bucket. And the orchestrator has to be sure that a certain sample of data is being routed through this pipeline, through the network in the correct fashion so that it goes through every single layer in the correct order, and then it goes back through the network through the correct people so that so that learning can proceed. So this is a big part of the IP that we've developed around this. It's a very complex scheduling problem amongst some other things as well. And basically, this is the interface to the brains of it. And you're absolutely right. I mean, a product vision or realization of what we're doing is one where people can basically have training as a service, where they come to us and we say, okay, we're going to articulate your needs as a customer as a specific training run with this model type, with this data type, and a bunch of other configurations that are necessary to make it work. With that, the miners are all going to be told, hey, you're working on this model now in this layer, processing data in this way. A second point that I'd add to that is it's not enough for the miners to just process the data. They also need to periodically share their results with their peers. They're in the same layer of the network. This is what we call the merging phase of the network. And the orchestrator is also responsible for sort of raising the flag and saying, okay, we're going to pause training. Now we're going to share our results. And now we're going to go back to training. And we basically cycle through those two stages in perpetuity, which is how training proceeds.
No corrections there, Felix?
Sounds all good to me, yeah. I mean, really, like, a simplified way to think about it is just a miner more or less acts like a compute unit that takes some data and pushes it through the part of the network that miner is responsible for. So, apply some expensive computation to it using a GPU. And the orchestrator coordinates what piece of data goes to which miner and where they forward it. So it's really just taking care of the entire coordination of the system, who takes what work and where to send which results to then end up with this properly trained model at the end. Yeah.
Okay, so maybe you guys can correct my understanding then. There's each layer like that, and then the S3 buckets sit in between each layer And that's where the orchestrator comes in, is the routing of data between each layer.
Pretty much, yeah.
Yeah, I think one thing I'd add to that, Grant, is so that the miners communicate directly with the S3 bucket. The orchestrator provisions them with a special URL that authenticates that they are the owner of the data that is about to be uploaded. And that's really important so that we can keep track of where everything is flowing. If they just had direct access and it's like a self-serve buffet, there's a few unwanted things that could potentially happen, whether it's collusion or oversampling. Maybe all the miners are going to try and get the same sample, which is just wasted effort. So the orchestrator takes care of assigning miners to samples. And once they're given a special link, the link points at a specific file or a specific destination where they're going to upload or download their results from.
And the validation process for this is what you guys call a shadow audit. And that's, from my understanding, after a miner processes that data, a validator would come in and essentially just take their seat and try to do the same thing, and then see how far off the miner is.
Shadow audit sounds a little bit like a bad guy on Harry Potter. It's like Voldemort's sidekick. Shadow audit. Yes, you're right. Do you want to add any color to that?
Yeah, I think just one thing to add is this is a very easy way of doing it. It's quite safe. It means because we're doing exactly what the miner does and is reproducible, we can just check that the work that the validator does is exactly the same as what the miner does, which is kind of completely secure and makes exploiting this really hard. But it's also very inefficient because you have to run a lot of compute because you have to redo everything that your miner does. Of course, we only spot check it, so we only check maybe 10% of all the miners at a given time. But it's still, like it's quite a lot of overhead. So just earlier today, we spent a couple of hours brainstorming better ways to do this, and we're getting somewhere. So this is subject to probably be changed over the coming month or so, with kind of a more sophisticated way to check the network with less overhead. But yeah, for the moment, that's exactly how it works. So
yeah, this is really the core of the whole thing is sort of contingent on how well we can validate it. And this is a unique problem to Bittensor, right? There's some other pretty prominent projects out there that are doing different versions of distributed training, data parallel mostly, well, data parallel entirely. But in those cases, they don't have to worry about adversarial actors. So validating is, of course, a core component of Bittensor. And I would say the Bittensor community has kind of discovered a few primitives, a few basic patterns that work well in practice, but they can be quite inelegant and quite clunky. And I think spot checks are they're the gold standard, right? A spot check means I redo exactly what you do, but maybe I just do it, infrequently. And the nice thing about it is there's no doubt in my mind that when I measure your work, I know if it was right or wrong. So it just the measurement ambiguity goes away, but it's expensive. Because if the validator just redid everything the miner does, then you've got no benefit of having a network of miners to outsource the work to, right? You just have to match it. So it's pointless. So spot checking is necessary because it allows you to offload, and to Felix's point, the miners do 10 times more than the validator measures. So you kind of have this nice economy of scale on that side. But what we're really looking for, and I think what Macrocosmos does quite well, is we're always looking for clever asymmetries where you can determine if work was done well without just doing all of the work, And the day that zero knowledge proofs and ZKML is mature, I think Bittensor will gobble that stuff up because that's kind of the thing that we want. But where we are right now is we have to think very carefully about a specific domain, and we say, okay, I want the miner to do all of this work. I don't want to have to redo all of it to verify it. So what's the cheapest way that I can reliably detect whether the work was done well or not? Usually this requires heuristics. There's a few clever things that you can do, but right now we've survived launch. We have a pretty simple but robust approach to validation, but this is the place where we're working the hardest right now to find out how, if the validators were outnumbered 100 to 1 by miners or 1,000 to 1, what could we do to allow them to keep up with the network so that they don't just slow everything down to a halt? And that's really the North Star for the project.
What are the future iterations? What do you think those will look like for the validation process here?
One thing that we talked about in the white paper is a technique that we've called CLASP. So CLASP, it relies on basically, because miners don't know whose data they're processing, because you've got this coupled system arranged in layers, you're basically picking up the output of the previous layer. Someone in the previous layer has an output, you take it as your input, and so on and so forth. Now, miners do not reliably know whose work they've taken on, and they're going to continue. And as a result of this, the CLASP is built on the fact that you basically have all of these sub pathways that can go through our network in the way that it's designed. And if you run this for long enough, you can actually detect pretty consistent patterns, like an anomaly. So if a miner is a bad actor, what it will tend to do is it will take that data and it will process it in an undesirable way, which will have very serious downstream consequences. The way that we measure that is called loss. Loss is like the error rate of the model. If they do something unwanted with the data when they process it, or they just output zeros or random numbers, the loss will be much higher than it should be. And statistically, you get enough samples of this, you start to see very quickly that a specific individual, no matter who they're paired up with in all of these pathways through the network, anything that touches that person comes out with a very high error. And that's the basis of CLASP. What we really like about it is the validator, all it does is it just reads some logs. Basically, it just reads a text. It's like an audit model. You just read a text file. You've got, you know who was in that path, the final error or the loss of that path, and the result, repeat a few thousand times, and you can clearly separate between what's good, what's bad, and what's ugly. So CLASP is, I think it's pointing in the right direction. We actually had a good session today where we're refining the idea further, and we're thinking about the next expression of that. It's a little bit half-baked right now, so I'm a little bit... I'm a little bit reluctant to go deep into it, but we think that CLASP is not just one technique, but a family of techniques, and we think we've found a version that's better and works in both directions, with what we call forwards, where the sample starts as the page of the sentence, comes out as an error, and backwards when the error is the learning signal for all of the layers as it goes back up the network. So we want something that's bidirectional, highly robust, and very asymmetric, so that validators can just scan through a document and they say, this guy is not contributing enough, and he can be rewarded or penalized accordingly.
Maybe also to just add one more thing, which we're also kind of focusing a lot of our research on right now, is with this initial approach of trying to replicate exactly what a miner does, you need to know everything about that miner to be able to exactly replicate them, right? So you need to know exactly the weights of the model, the optimizer states, like the gigabytes of data that each miner has locally, which they need to currently share at regular intervals. And uploading those huge amounts of data just makes the training really, really slow. And there are some established techniques in which allow you to just compress this data down to sharing only a fraction, so like less than 1/500th of that data, which of course leads to like huge speed up. But because you then can't replicate exactly what the miner was doing, because you don't have all the information but just kind of this compressed version, our current validation systems struggle with this. So that's all kind of how having this more sophisticated validation with CLASP will then allow us to just also speed up the training process massively by using already existing kind of state-of-the-art compression techniques.
Mm-hmm.
And CLASP sounds like it's something that wouldn't be possible at launch. It's only possible once you have enough historical data to then be able to detect these anomalies.
Yeah, so when you initially start training the model, the losses kind of, all the predictions are completely random. So the losses as good as just sending through random numbers. So of course, that means you kind of can't detect the difference between someone actually doing what they're meant to be doing and someone just sending through random numbers. And then kind of as the training run matures and your loss goes down, suddenly if someone's doing the right thing, their error rates will start getting lower and lower. So when then someone sends through random numbers, the difference will become increasingly big, and it'll be increasingly obvious to trace when someone is cheating. So that's exactly correct. Yeah. You need some warm up for CLASP to start working out.
Yeah, the name is actually an abbreviation, or it's an acronym. CLASP stands for the Contribution Loss Assessment via Sampling of Pathways. The sampling of pathways is this random routing mechanism of data through the network, and the contributions of losses is about how much impact miners in the network have on the overall error of that for that particular sample that went in. So that really encapsulates the idea.
And you guys have, I think, 128x compression on passing those activation functions forward. Why is this so important? Is it just for speed of a training run, or is it limitations on the size of that data that you're passing?
I'd say first and foremost, it's a speed concern. Data compression, if there's no loss in the data compression, it really just allows you to transfer data more quickly, right? You just have less data to send to someone else. So one of the challenges with pipeline parallelism, and most likely one of the reasons it hadn't been done before, is because unlike in data parallelism, where you have to share across with your peers your current state in that synchronization process, we have an additional requirement that we have to send these so-called activations between layers. So there's a lot more data transfer than in the data parallel paradigm. So one of the major issues with that is you have to send activations all the time. The network is just constantly shooting activations across. And if those files are really large, we just can't process data fast enough to train this model in a reasonable amount of time. So the 128x compression is because we basically modified a very well-established and popular architecture called the Llama architecture. We found that there are sort of the interfaces between the layers. Remember, the miners have their own layers, and there's a lot of data that has to go from here to here. And basically, Alan, shout out Alan, our research lead, he realized that there was a way to reduce the amount of data that goes between all of the adjacent layers in the network by modifying the architecture itself, which still, it would appear, it still enables the model to train very rapidly. And our results have been very promising when we've done some baseline experiments on that. It allows the basically training to proceed much more quickly in a way that we weren't able to do this by simply quantizing or doing some quite naive tricks to reduce the amount of data there. The best thing to do is actually it's kind of like you carve out a different river basin and just let the water flow in a different way. And these models just are, they just want to learn. And if you give them the right framework to work within, they're very good at it.
And also to add again, like right now, the core limitation of the system is internet speeds, right? So if you look at how much time is spent uploading various files, so weights, activations, whatever it is, compared to how much time is spent processing those files, that you'll see that there's much more time spent on the uploading compared to the processing. Ideally, we want that to flip, right? We want to have 90% of the time actually being the learning part, and then 10% of the time maybe being uploading and downloading data and sharing things. And on the activations prior to the paper that we wrote, kind of the best compression rate that was found was about 10x. So pushing that up to 100x already like sped it up by a lot. We'll probably need another 5x to get to this point where the majority of it is actually processing time compared to upload times. So even now we're still looking at ways to improve on that, but yeah, this kind of compression is a key issue across like everything that we do in the system. Yeah.
There's a really beautiful truth that lies beneath all of this stuff, which is so actually I want to also acknowledge the work of another team out there called Proudest. They released their white paper very shortly after we did, and they found we actually had this like 11th hour rush where we were just about to launch a subnet. We had the white paper 40%, 30% done. Then those guys announced our white paper after 3 years of work. We're going to now push this on Monday. And it was like Thursday evening. And we just thought, like, what we don't want to happen is for our results and our techniques to be in question. If those guys publish first, there will always be a doubt if we came up with this ourselves. And that was really important to us. We put a huge amount of work and time into our technique. So we pulled an all-nighter. It was crazy. We got our white paper out. We shared the techniques that we had. We've improved things further since then, but we frame it as a technical primer for launch to emphasize that this is the blueprint, but by no means this is not the final product. But what I want to talk about is those guys actually found a different solution, which is better for everyone. The world now has 2 candidate solutions for this particular problem, and I think what we ended up doing inadvertently was a very top-down empirical study I wouldn't say entirely top down. Like Alan wasn't just like fumbling around with a blindfold on. He has very good intuitions about how these things are meant to work. And he figured that the model has a lot of parameters, right? It has a lot of space to pack knowledge and representations and patterns within. And the question is really, does it need all of that space? Is all of that space fully utilized, or is the model actually doing something which is, doesn't require all of that space, to put it simply? And so we landed at this idea of we're just going to give it less space and we're going to let the model figure out how to use the space more efficiently. That in a nutshell, that's what we did. What Proudest did is they came up with a very beautiful theoretical grounding for the same phenomenon. And what they observed through a much longer and more technical paper than ours, I would say, is they basically showed very definitively with a series of training runs from start to finish, very good outcomes. They basically showed that just the training process itself tends to force the model to find representations or find sets of parameters inside of itself that are as compact as possible. It doesn't reduce them just down to like one parameter because you just can't make a good model with so little expressiveness. But it turns out you don't need, 70 billion parameters of information to do a lot of good stuff. So their approach and our approach are very complementary, and they basically proved why what we did works. So it was a really interesting sort of intersection of two very different teams coming at it from quite different angles.
Another piece in this puzzle, I guess, is the back propagation step. And your guys' solution to that, or your implementation on that, is butterfly all reduce. I'm not necessarily completely sure how it works. My understanding is there's the vector gradients, and then you split that in half, and then you just swap with somebody else, and then this makes everyone have the average of all the gradients, so everyone's on the same starting point. I'm sure that is a very flawed explanation, but you guys can definitely correct that.
Yeah, so one thing that's very confusing is that there's two separate papers that both present something that they call butterfly all reduce. And one of the papers is the one that you're describing. What we're doing is the thing that the other paper does, which super confusing. But what we do is probably quite a lot simpler in that we say, let's say we have 10 miners. They each have some vector, some list of gradients that they need to share. So then we go and we say each miner basically splits their list into 10 different sections and uploads those. And then the first miner is responsible for merging together or averaging the first section from everyone else. Second miner is responsible for the second section from everyone else, and so on, which means that everyone uploads their weights once. Then the first miner uploads kind of this first section 10 times, kind of another set of weights, averages those and uploads them. And, the second miner does the same, and so on. And then in the end, you have, because every miner uploaded kind of, 1/10 of the average weights, you get this full set of weights reconstructed. So what's really neat about this is that no matter how many miners you've got, the amount of data that everyone needs to transfer actually stays constant, because if you've got 100 miners, suddenly each miner is only responsible for 1/100th of the gradients. So this basically allows you to scale infinitely big without ever having to increase the amount of data that you need to that each person needs to transfer or needs to download. I don't know if you want to add to this, Steffen, but
I can try and come up off the cuff with some kind of analogy here. It's a really clever distributed systems technique that's been used extensively in a lot of contexts, not just model training, but it's a really efficient way to share information across a network. We use an analogy of color. So imagine I have whatever, 3 cards. Okay, I have a red card, blue card, and a yellow card. And Felix has 3 cards as well. And let's say we have Will somewhere in the background, and he has 3 cards as well. And what we want to do is compare all of our cards, and we want to merge them together. So there's a lot of ways you can do this, but it turns out the most efficient, and what Felix has described very, very well, is let's just say we nominate Felix and we all give him our red card. Okay. And then we nominate Will and he gets all the blue cards and I get all the yellow cards. Now, let's say that what I'm going to do now is some kind of local, I'm going to do some work with my 3 yellow cards. I'm going to combine them together. Maybe they have a number on them. I'm going to basically add the numbers together on the yellow cards. He's going to add all the red card numbers and Will's going to add the others. And then what we're going to do is we're basically going to share the result, because now I have the merged copy of all the yellows. He has the merged copy of all the reds. And Will has the merged copy of all the blues. And then we can share them back again. And this just requires way less communication than everyone passing it to the left, or something that you might think intuitively is a simpler, more straightforward approach. Butterfly overreduce turns out to be, it's log n complexity. It's log n complexity.
Oh, no, you can it's constant.
No, it's constant n complexity. That's right. Which just means that especially when there's a lot of data transfer involved, it makes the process way faster. And for us, we also found a way to effectively create fault tolerance and resilience within the system as well by adding redundancy to that. So I'm not going to try and procure an analogy about the redundancy part of it, but the main thing here is, if instead of Felix being the only guy with all the reds, imagine we're a big group of people and I make sure at least 2 people have reds, information on the reds, and then they can both report them. And now if the 2 of them are inconsistent, I also have some awareness of whether there's someone exploiting or not doing the work correctly. So butterfly overreduce with redundancy allows us to merge efficiently, but also be very sensitive to any bad actors that are trying to drive this thing off the rails, which of course is very detrimental to the progress of training. If someone uploads bad weights, they've polluted the work, and if basically, they're diluting the effort of everyone because they're incorporating that bad information into the network. So the redundancy factor is super important for that as well. Yeah, and we're proud of it.
And this has been almost a full redesign of Subnet 9 from what it used to be. A lot more complexity in the architecture. What are you guys most proud of in this essentially rebuild of Subnet 9?
I'm going to go first. We did something that's never been done before. We did something that no one has ever done before. I mean, how is there anything you can be prouder of than that? There are so many brilliant people in AI, and I think the world is becoming more and more aware of the importance of, let's just say, alternative ways of creating the next generation of AI, so it's not captured by very powerful individuals and companies. I think that the fact that we were able to assemble a team, we did a 2-month literature review where we could pretty much have verbatim recited the top research papers from top to bottom. We went really deep, we worked really hard, and the team really came together, and we were able to be the first. Like, I'm just, as a scientist, like, so much of research is about whether or not you got there first, for better or worse. So we're really proud of that. There's so much more to be done. All we did is we planted a small flag and said Macrocosmos was here. The results will speak for themselves. But personally, we took a challenge that I think a lot of teams have avoided just because of the very apparent complexities that come with it. Like, there's just what a I don't know, complex maze of information that you have to make sure flows smoothly, otherwise the whole thing crashes and burns. And we were able to put this thing together in 2.5 months from start to finish, and it was just so ridiculously ambitious, and we pulled it off.
Yeah. To me, it's also like it feels less like an incremental step in research, but it's kind of a fundamental new system that I think for the last few years, it was companies didn't even attempt to do because it seemed too complex. Like the standard federated learning, there's now a few companies that have gone for that and that have built systems, and a few subnets also in Bittensor. But the idea to go pipeline parallel, just not even in a non-trustless system has this been done. And to be able to pull this off for the first time and to immediately do it in a trustless system and to actually have people have it work, like loss going down within a week of launch, it has been incredible with how the team came together with this. That's really that.
And then what does success look like for IOTA, Subnet 9? In 2 years from now, 3 years from now, maybe 3 months from now? I don't know the timeline here, but What is success for you guys? How do you define it? What does it look like?
For me personally, we're just really focused right now on tuning the design. We're probably going to rewrite the code base in the next couple of months. It's research code, and research code basically means you move fast, you break things, you just get to the results. But we need to properly harden and productionize what we have, which means that we also have to throw away some of the parts that aren't serving us, double down on the aspects of the design that are really powerful. So I'm really excited. I'd say the next couple of months, it's about really refining the idea, breaking it down to the simplest articulation as possible so that it's as powerful as possible, but no more complex than it needs to be. In terms of concrete results, we launched with a 15 billion parameter model. That is extremely ambitious. It's it's the largest model of its kind to be trained in this fashion. Of course, we want this model to be trained successfully to completion. We're starting to get a clear sign that we've got the right configuration. Like just tuning a lot of this stuff is not something that, you can't transplant what you read in the literature to what we're doing, because everything actually has a different sort of sweet spot when you're doing it under this design. Like everything has to be recalibrated. So we've been doing a lot of that calibration for the last couple of weeks. I want to see this 15 billion parameter model get trained. We've been doing a lot of warm-up experiments. Every couple of days, we restart the run. We try and make it really clear to the community and the wider world that what we're doing right now is we're not doing the training run yet. What we're doing is sharpening the tools, refining the design, because when we start the training run, it takes weeks and weeks and weeks to train this thing from start to finish. And if we have a better idea about how we can make it 2 times as fast, it's actually very prudent for us right now to say, okay, we've seen how quickly it went down in version 1. We've seen what happened in version 2. We're on version 40. We're on version 40 and we're 2 weeks in. So what's important right now is really running the experiments, getting the results, iterating as quickly as we can so that we know when it's time to press go and actually let this thing train for an extended period of time. We're really confident about the design.
And to add a little bit more, I guess, at the longer term vision, I think there's 2 clear directions that this will be moving in, which is, firstly, currently everyone who's contributing has to have at least an A100. That's still pretty limiting. We will be able to move down to much smaller machines, up to the point where hopefully you'll be able to take your MacBook with 16 gigs of RAM or 32 gigs of RAM and join this training run to just make it more accessible to more people. And maybe also break through the 256 miners per subnet limit and really take this large scale. So if you think of a kind of folding at home scale. So that's, I think, the one direction of optimization. And the other direction of optimization is the size of the model we're training. Because as opposed to other methods where you're bound to how big is your smallest miner, we have no boundary on how big we can make the model. Like fundamentally, we could launch a 100B model. It just take much longer to train. So there's a lot of work that needs to happen to speed up this training so that a bigger model can be trained in a reasonable time frame. But you can also start blowing up this model size up until you're competing with the Metas and the OpenAIs of the world. So I think that's kind of really the super exciting long-term goal to once you reach both ends, tiny hardware requirements, but you get to train this absolutely state-of-the-art big model.
Yeah, I can't emphasize that enough. Like training a 100, 400 or above billion parameter model is just not possible with any other distributed training network in the world. Because every miner would have to run that entire thing. They would need a small data center of their own. Whereas we're taking this from we're building up with the atomic units of this. Instead of having, 10 data centers that are collaboratively training the next generation of AI, you have 10,000 MacBooks. Very different picture, very different framing, very exciting, much more democratized. And of course, we do this on the playing field, permissionless in an adversarial environment, which means this thing, I don't need to whitelist my friends, or I don't need to choose who's allowed to play the game. This thing is designed from day 0 to work in an adversarial environment, which means that anyone can join the network and they can be compensated for doing something that I think is a really important contribution to the field. You can have, and then there's this, we've thought as well about licensing models. For example, if anyone that contributes to the training of a model, they also have in perpetuity a license to use that model both personally, as a hobbyist, and even commercially. So there's a really interesting way to do IP capture. There's a great way to incentivize alpha holders by giving them additional benefits to the models that are trained. And yeah, the productization of this subnet will happen once we're really confident in the design. But we've done multiple things in the previous Subnet 9 architecture, things like having very custom blends of different data sources. This is a very important part of training powerful models, is you don't just give it a big soup of everything on the internet, but you actually want to very carefully curate certain types of data, whether it's math and programming or reasoning or multilingual, and the ability to change that. And also like long form, short form, these things are very important inputs to how well the model is going to perform at the end of the day. And we built basically an entire set of tooling in the previous version of Subnet 9 that gives us that precise articulation over how the data goes in, when it goes in. So we're going to be using a lot of that. We've also already solved a lot of the problems around how do we have 10 different models training at once. As long as we have enough workers on the network, we could have customers that are coming, they want a bespoke architecture, they want a next-gen architecture, they want something that's multimodal. We've already thought a lot about this. We've already demonstrated a lot of this is possible. We've been sharing our results. We've been writing reports for a year and a half. So we're excited to sort of bring a lot of that knowledge into this current era and use that to charge up where we're going as well. We're really confident in this. It's good.
And then I got one last question for you guys today. And that is, what advice do you have for teams, Subnet or otherwise, that are trying to be first and take that 0 to 1 step, go from theory to reality? What advice do you have for those teams or people out there?
I can take that.
Yeah, go for it.
A mentor of mine told me a few years ago that in the world of startups, aspiring to create an incremental gain is just a death sentence. Part of the business model of venture capitalism, as well as just the sort of selective pressure of good teams and good ideas, is you need to have your moonshot. I really believe in this idea of like a team needs to have a dream, and that dream needs to be almost by definition basically unachievable right now, but they have a set of very concrete actions that they're prepared to take to demonstrate that it's possible. And going from 0 to 1 is hard. There's no precedent. It's freaking scary, to be honest. But I think going from 0 to 0.1 is, in practice, you're just not going to have the moat. You're not going to be able to sell people on the dream as much. Like a lot of it is just the energy that you create. The passion is contagious. People can feel it. And yeah, go big or go home. It's just what we do.
Felix, anything to add there?
I don't think so. I think I mostly agree with this. I mean, like for me, I came into Bittensor with the idea of wanting to do this, and I pushed for this for like I think I annoyed you guys for close to a year to get to work on this, and like it pays off, right? Like the entire team around this was incredibly motivated. I think if this would have been a different project, if this would have just been, let's do the standard federated learning, let's, try and instead of training, well, pushing the model size a little bit, people just don't put in that amount of work and don't spend all night thinking about those problems. So I think just having a big goal, it just, you're much more likely to then actually follow up on it than trying to do something small. So just don't get the same degree of motivation and the same degree of passion for it.
And I think the last thing I'd add as well is in an industry that's moving as fast as AI, if your North Star is just an improvement, a marginal improvement in what already exists, a more well-funded team will almost certainly outcompete you either in the short term or the long term. Just because there's just so much capital, so much attention on this AI, human effort right now that I think you have to be completely obsessed with a very specific problem and ready to throw everything at the wall.
I think maybe one last thing as well is like with how fast things are moving, it's actually counterintuitively quite easy to find novel ideas. Like if you have a very established field where there's been incremental improvements for the last 10 years, like the chances of you finding a breakthrough are, fairly minimal. But currently, like if I compare the landscape and the knowledge we have in AI right now to, like, say, even a year ago or 2 years ago, you're looking at completely different worlds. So you just have the opportunity to quite easily, as an individual contributor, or with like a small team of 3-4 people, to come up with something that's like truly novel, which I think is, if you look at the history of AI, is quite like a unique spot to be in, because like things just never moved this fast and there was never as much opportunity.
Yeah, I mean, my background was in high energy physics, nuclear physics, which is a very conservative, slow community where, through a painstaking process that you've got cycles of 10 years, or at least the clock ticks in units of PhDs. So everything is just really, really slow. And you're absolutely right. Like right now, things are moving so fast. It's exciting. It's exhilarating to have doors that open that were just unthinkable. And I think when we were standing at this door, and there were a number of occasions where the team were like, we shouldn't do this. This is impossible and irresponsible. But I think the lesson of history is often like, I sometimes try and imagine looking back today, 10 years in the future, when if we didn't do it, someone else will have done it. And it will have probably been solved definitively in 10 years. And when you look back at it, it's just going to look like it was inevitable. Of like, yeah, we just weren't thinking about it in the right way. Maybe it was a compute problem or something, but in most cases, it's like, do you have the right frame of reference to think about this in the most powerful way that you can? Because like, all of the dominoes fall eventually. I'm a firm believer in that. Whatever it is, you just like, it's just a matter of time. And the thing that usually knocks those dominoes down is just people that are absolutely obsessed with that problem. And if you're unfortunate, you're a little bit early. And you know what? That's too bad. Keep at it. Keep working hard. Being early is not a bad thing. That means that your senses are very well tuned to a good problem. And hopefully you've acquired a lot of expertise and forward-thinking patterns on that topic, even if the technology wasn't mature enough. But, mark my words, like the things that we're struggling with today, in 10 years from now, people are going to be like, this is solved. If not solved, there are very practical, scalable solutions to it. And the question is like whether or not you allow yourself to be open to that possibility, or whether you're going to wait for someone else to make it obvious.
Felix, Steffen, thank you guys for coming on the podcast today. It's been a pleasure.
Thank you for having us.
Thanks, Greg.